Okay, welcome everybody to day 3 of the Scripps grad Organometallics course. You administrative reminders, end of this week is the deadline for Wikipedia project topic selection. So thanks to those who've already engaged with myself and the TAs in person or over email to discuss potential ideas. If you haven't done so, please start thinking about it. And we're happy to bounce ideas back and forth, just drawing on our own experience about what topics might work or not work or make suggestions. So the earlier you initiate that conversation, the better. Also, there was a question just before class. If students want to submit any quotes of the day for consideration, you are welcome to do so. You can email me or the TAs directly. You would like to inspire your classmates? Okay, we will pick up where we left off, and where we left off was a discussion of hapticity and the consequences of haptotropic shifts in the context of electron counting. Were there any questions from last time before we jump right in? Okay, feel free to interrupt me. We've got about a page of notes here to wrap up what is formally the day 2 lecture notes, and then we'll jump into day 3. So last time I mentioned we left off with hapticity, this ability of a given ligand to adopt different coordination modes where contiguous atoms are coordinated and able to donate a different number of
Jerry, I have a question.
Yes.
Sorry, how is hapticity actually counted? Is it like from a crystal structure or like experimentally?
Yeah, that's a great question. So just from a molecular formula alone, you wouldn't necessarily know the hapticity of a given ligand. There are a couple analytical readouts for hapticity. One, I think, is the one you alluded to. If you have an X-ray crystal structure, then you can determine the hapticity. It can often be read out just by NMR, and sometimes the hapticity observed in the solid state may not always be what's observed in the solution state. So the example here is metal benzyl, but by analogy, metal alleles have the same property that the eta-1 and eta-3 forms have pretty diagnostic NMR signatures in proton, or in some cases phosphorus if you have phosphine ligands. And then classically, people would read this out by IR as well, although that's less common these days. Yes.
Is the favorite haptotropic isomer just depend on the metal and the ligand environment around the metal?
Yeah, that's a good question. So in case anyone didn't hear, the question is is there any way to know, if I understand your question correctly, is there any way to know a priori what a favored hapticity would be? For example, in this benzyl case, would it prefer to be eta-1 or eta-3? It's a confluence of factors, and we'll see a case in one of the problems of the day today where actually multiple hapticities are existing in the same molecule. So it's not so cut and dry. Often in the context of catalysis, this ability to toggle between states is important. So that is telling you right there that thermodynamically they can't be that far apart if you need to be able to sample both states. So the short answer is I think you would, like, if you're just given a molecular formula, you'd need some hints for how to represent it. One hint would be if you're getting to very, very low coordination numbers or low electron counts, then that's a signaling element that it would probably adapt a higher hapticity in order to be more coordinatively saturated. So let's talk about bridging ligands. And one of the features that you'll see throughout the class is that there are certain ligands that commonly bridge multiple metal centers. You'll get a sense for like these usual suspects, so to speak. Two common ones are halides and hydrides. In addition, alkoxides, hydroxides, phenoxides are common bridgers, and those all fall in the category of X-type bridging ligands. So in the case of mu2 bridging, two meaning it's bridging two metal centers, you would typically see something like this. And to me, I always like to connect this to things that I know that I'm a little more familiar with in the main group. So if I just see this, I'm kind of wondering what's the bonding depiction really look like. One heuristic, one way to think about this in the case of halides, at least to me, this is clarifying. If it's not clarifying to you, forget about it. But I like to think that one of the lone pairs of the halide that's bound to the metal on the right can just engage in a dative interaction with the metal on the left. And to me, that feels comfortable. So that can be represented in this way. It can be represented in this way. And then equivalently, it can be represented in this way. And because a lot of times bridging interactions come in pairs, not always, but often, which way you represent it turns out to not matter. So for example, this would be a case where however you count electrons per metal, you'll get to the right answer. Now, in the case of hydrides, it's a little bit more wonky because you don't have lone pairs on hydrogen that can form this dative interaction. So the way to think about this is that actually the filled sigma bonding orbital is itself serving as the source of electrons for the dative interaction to the metal on the left in this case. And my pen may have run out of batteries. It's okay. And so again, all these representations are just different kind of formalisms that hopefully help, that are clarifying. And if they're not clarifying, then you can represent it in a way that's clarifying to you. Now, on the right, we have a different case. So all the cases on the left are the bridging element is an X-type ligand. Another common bridger is the CO ligand. And what's different about a CO ligand is that it's an L-type neutral donor. And so, whereas in the examples on the left, in terms of electron counting, you can count them as denoted in this top right example. You can count an X-type ligand for one metal and an L-type ligand for another metal. In either case, you're getting 2 electrons per interaction per metal. Now, in the case of the neutral bridging CO ligand, because it's neutral, it's only bringing 1 electron each per metal in the anionic counting mode. I think if you don't adhere to that and you count each of those bonds as 2 electrons, you will start to get to very strange electron count, 19 electrons and so on, and you'll know something is amiss. So again, I want to make this point that does this fall out of first principles that a bridging CO should count for 1 electron? No, remember, this is accounting, this is formalism. So we do this, and if nothing else, you can just remember this rule in the anionic counting mode that a bridging CO gives you 1 electron apiece per metal, and that will do it. And you don't necessarily need to think about it more than that. But really, if you think more deeply about it, it's just a consequence of the fact that it's not charged, and thus the electron inventory works out this way. We've shown some examples where metals can, where ligands can bridge two metal centers, or one metal can have two bridging elements, but of course there are higher levels of bridging. So here's an example with this ruthenium complex is forming, possessing not two, but three bridging chlorides. And its bimetallic core structure. And there are innumerable examples of bridging interactions. And when you build up from bridging interactions, then that is, you can think of that starting to be the starting point for polymetallic clusters. So we recently had a paper together with Rudy Jazzer, where we use these multi-center two electron bonds to template assembly of clusters. So you can think of these bridging interactions really as the starting point for polymetallic clusters. Okay, we'll switch over now to, if you still have it, problem of the day worksheet number 2. And if you don't have it, that's fine, because I will pull it up. We've got a couple problems of the day to finish up. Okay, so we've got problems of the day 3 and 4, both back to back here. And this will give me a chance to get a little charge in my Apple Pencil. So I'll read through these. So thinking back to problem of the day number 2 from last time, you'll remember that we covered Paulson and Kelly's seminal synthesis of ferrocene. So now we're using ferrocene as the starting point. And what we're going to do is a reaction between ferrocene and concentrated sulfuric acid, a workup where we treat whatever is formed from that with ammonium hexafluorophosphate. And what we're looking for is the structure of the product, but then also the full electron counting, meaning coordination number, metal oxidation state, d-electron count, overall electron count for ferrocene, the starting material, and the product, whatever you come up with here. And then problem of the day number 4 should be pretty straightforward. It's an electron counting exercise for 3 different late transition metals, a third row metal, a second row metal, and a first row metal, respectively. So I'll leave this up. I'll give you a minute or 2 to think about it, and then we'll jump right in. In case anyone's feeling left out about being called on, I dug to the bottom of the cup today, so Mix it up. Okay, well, you're still working on it. I don't expect anybody to have finished yet, but let's just get the reaction details of the starting material and the product up there so that everybody's on the same page here. Okay. Cecilia, so what do we think might happen under these conditions? So we have Ferrocene as the starting material. What might happen here?
Is it possible the sulfuric acid loses a proton, coordinates to the iron, forcing one of the cyclopentadienes to slip?
Oh, okay, that's an interesting interesting proposal. So we could view this as a H plus, and then I think your proposal was, which I think is definitely plausible, would be something like you're recognizing that these CP ligands are electron rich in character. And so you had the potential to react them with electrophiles. I don't know what happened there today. Might have just been a physical connectivity issue. Okay, there we go. So I think you're proposing something like that. Is that correct?
Yeah.
Okay, and then what would be the role of the next step? The next ammonia, F6. In this case, you would have this as the counter anion. Step one. Then if I'm thinking what you're thinking, or you're thinking what I'm thinking, then you'd have this as the product of the second step.
Is it possible for the phosphorus to associate with the iron?
Could you say that one more time? The phosphorus.
To coordinate with the.
Well, that's a good question, but these specific types of ligands are often referred to as weakly coordinating anions. So they tend to like to be in the outer sphere because they don't have a lot of high charge density at any one given point on their surface. So I think this is reasonable to think, but you might feel uncomfortable that this adduct may not be very stable. And whatever you're making needs to be pretty stable because it has to survive in concentrated sulfuric acid. Anybody get anything different? Alex?
Can the ferrocene serve as a single electron reductant of the proton so that you get ferrocenium?
Aha, okay, so ferrocenium, is that what you? So we're getting to a charged species, just like Cecilia proposed here. But what Alex said is effectively, this is just losing an electron, and so the ligand here is not involved, but the metal is engaging in the redox. Now, what is the oxidant here, Alex, or how did you think about that?
The oxidant is just like the proton, basically. So like I'm thinking of it like two equivalents of ferrocene react with basically two protons to give H2.
Okay, so that would be, so then what would happen is you would lose H2 gas effectively each proton is accepting electrons, well, that would be half, it'd be half. For, I think, this is actually what you said, right? Half. Which I think is reasonable. And then what would be the alternative? How else can sulfuric acid serve as oxidant? Yeah, Kevin.
Can we just make iron hydride?
Oh, iron hydride.
It just gets protonated, right?
Yeah, and then that would, so I think that's kind of where Alex was thinking is you protonate the metal center and then two of those are going to find each other and there's going to be bimetallic H2 reductive elimination, something like that. Any other thoughts? How? So I think the key thing is that in this case, H2SO4 is serving as an oxidant. One way to draw it would be as Alex described, and then I think another way that you could push electrons would be,
Yeah, sulfate. This,
yeah, I think if I heard you correct, basically it's like your driving force is going to be loss of SO2 gas. And so you can play around with pushing electrons to get to that that solution, but that was the other possibility here. Okay, but we don't need to get too, and actually, even though this chemistry is very classical, some of these mechanistic details are still not really well pinned down. How does concentrated sulfuric acid serve as an oxidant for organometallic complexes? It's quite complex, not straightforward to study. So I don't want to derail us too much on that because a lot of that is still in the year 2025 black box chemistry. But let's take a shot at the, so thanks Celia, thanks Alex, Kevin. Let's take a shot at the electron counting. Julian, what did you have for the starting material?
So there would be, what's the electron count on iron? D10. Oh, sorry,
It's D9.
it's 8. It's like that.
Okay.
Okay, so how about just the coordination number first? We've
Okay,
got
oxidation.
2 eta 5 TP ligands.
We can do the electron count first. I just didn't have the.
Oh, okay. So whatever you want to do first is fine.
Yeah. So if it's D9 and it has an oxidation state of 2, so it has.
Okay, so iron itself is D8.
Or is it D8? Sorry. So D8
Iron 0 is D8. And then you're
and it has
saying
an oxidation state of 2.
we have 2 X-type ligands. So let's just do this formally. We won't do this carefully every time, but each of these ligands is L2X. We said eta 5 CP. So 2 X-type ligands is -2 charge. So you're saying ferrocene here should be iron, the +2 oxidation state, which is D6.
That's right. So it's D6.
And then
And it's
you're
bound to
2 times
2 ligands.
CPs, each is L2X. So each is going to bring how many
Each.
electrons?
6 electrons per CP.
6 electrons
So 12.
for overall 18 electrons. So there you go. There's the secret to ferrocene stability, a stable 18 electron complex. Coordination number, if we're using this electron pair method, we'd say the coordination number is 6.
From the
Anybody
2
get
L's and
anything
1
different
S.
than that or have a question? Yeah.
Did we got periodic table in the exam?
Oh, good question. I've got good news and bad news for you. You will have a periodic table because you will write your own periodic table. As question 1 of the midterm will be to write the periodic table, at least the D block. And
Wait,
that
are you
is a
kidding, or-
long-standing tradition going back to even when I was a student. So And that, you'll have plenty of practice for that. I think one of the things that I didn't really believe when I was a student, but does turn out to be true, is that a lot of this electron counting stuff is very painful if you have to consult your periodic table every time. So, yeah, question one of the midterm, just like last year, just like 2 years ago, just like 4 years ago, will be write out the periodic table. And then, of course, you can use it as a reference. If you, so we don't want to like have errors propagate. So at the end, if you aren't confident with your answers, then we can grade it on the spot for you. The periodic table part. Yeah. It's not as, honestly, it's not as terrible as it seems. Probably you could already do like half of it, and the ones you don't know are tantalum and niobium and vanadium and sorts of things.
Gary, follow-up question to that? If we draw the periodic table wrong and then do a d electron count wrong.
Well, that's what I was saying. So if you're not confident, then we can grade it on the spot. Grade that on the spot for you.
Okay,
you
so I
have
can
the
write out the
correct-
periodic table, show it to you,
Correct.
then sit back down and continue. Okay, correct, we're good.
We won't have to, we wouldn't want you to be penalized multiple times for one error, essentially. Okay, and then Mike, how about ferrocenium?
It's the same less one electron.
The same, less one electron. Okay,
Yes,
so
it's
an iron 3, D 5, 17 electron. So 17 electron species, would we expect this to be happy?
Yeah.
No. We would expect, based on first principles, this to want to find an electron to get to the closed shell 18 electron state, and that is indeed its reactivity profile as an Albert-Speer single electron oxidant. Any questions on that? Alex?
In the solid state, does ferrocenium exist sort of as a monomeric unit, or does it form iron-iron bonds to get 18 electrons?
That's a good question. And you were alluding to the next section. I think your intuition there is spot on, but because of the structural features of ferrocene, it's hard for two molecules of ferrocenium to find each other, to find that interaction without incurring a lot of steric clashing. So even though it might be inclined to do that, I don't think that it does. Yeah.
Is the ferrocenium a very strong reductant? I just realized like I don't think I've ever seen it used as a reductant for standard
Oxidant.
oxidant as a standard oxidant for a lot of
Well, the ferrocenium redox couple is commonly used as a benchmark in
Yeah, that's true.
So I think that quantitative data is available, and I don't know what it is off the top of my head, but probably someone could look this up and we could jot it down if anybody can't find it. Okay, let's continue forward. Problem of the day number 4, more electron counting. So again, can't emphasize this enough. Electron counting, you can talk about abstract principles in isolation, but there's really no substitute for just getting your hands dirty and doing lots of practice problems. And so that's the spirit in which we will try to approach things. So let's take this. I think the simplest case here is the one on the left, this iridium one. So Riku, walk us through this one. Coordination number. 6. Okay.
Iridium 9 minus 3x duplicates of iridium 6.
So
Iridium 30, sorry.
yeah, so you're jumping ahead. So you got so let's count it out here. I'll just highlight here in red, where are your X-type ligands? You've got an aryl, you've got a chloride, and you've got a hydride. 3 X-type ligands. And then I'll highlight, again, I'm not going to do this every time, but just as we're getting started, your L-type ligands, pyridine, and 2 phosphine lone pairs. Oxidation state then is +3 iridium, and you said iridium is D9, so iridium 3 will be D6. You've got 3 X-type ligands, 3 L-type ligands. Each is bringing 2 electrons, or 12, for a grand total of how many? 18 electrons. Good. Anybody get anything different than that, or questions? Okay, so these last 2, we can maybe do more rapid fire style, or not, if anybody wants to take a minute and ask questions. Okay, Sam, do you prefer Sam or Sanya?
Sam is.
Sam, okay. How about this beta-6 arene complex?
I don't remember the electron of nickel, is
Okay,
it?
I'll give you a hint.
So I think that's nickel 0.
Okay, well, let's do the coordination number first, just because I already wrote it up. So you've got a eta-6 arene,
And I guess
and an NHC ligand. So we haven't covered carbene ligands yet. We will. I'll just give you a hint that this is a neutral L-type ligand. You can just think of it like a phosphine. So you've got L here, L3 here. So coordination number should be 4. Good. We said the oxidation state is 0. And then the electron count you already said was D10, is that right? And then we've got 1L, 1L1 ligand, 1L3 ligand. And so that's going to be 10 electrons. Sorry, oops, 8 electrons. Okay, so what was your total electron count that you got, Sam?
18.
Anybody get anything different from that? Mingxi,
I had 16 electrons.
okay, walk us through what you did differently.
I used the neutral method, so I started with palladium 10 electrons.
Nickel, 10 electrons, yeah.
I thought you were talking about palladium comments.
Oh,
Never mind.
all right,
Don't have the
all
same.
right, all right. And this specific example utilizes these extremely bulky aryl groups as a key design principle for catalysis. This comes from a joint paper between John Hartwig's group and our chemist of the day, who is, anyone would like to throw out a name? Not hearing any. Yoshi Nakao of Kyoto University. This is Kyoto University.
Are you sure she's Japanese? I think it's.
We're still on the problem of the day. Sorry, I'm creating confusion. Chemist of the day from day 2. Thank you. Famous, well-known for, among other things, aryl and nitroarene cross couplings, CC activations through dual catalysis, advances in nickel catalysis, and a prominent collaborator, formerly assistant and associate professor with Hiyama. Okay, last one. Now we've got two different palladium, chemically inequivalent palladium centers. We'll just do the one on the left, and I'll leave the other one for homework for you to see if you get something that's the same or different. Ningxi, since you were keen on this one, walk us through.
I had
Coordination number.
coordination number of 4 for both,
Okay.
16 electrons, palladium 2d8s.
Palladium +2, palladium D8, and then 4 ligands is 8 electrons. If you're counting, two are X type, 2 are L type. I'll do this again, just one more time to drive this home. We've got an X type here, an X type here, this one bridging, and then 2 L types. So in this case, you have 16 electron complex. Did this make you uncomfortable at all?
I mean, that's pretty normal for palladium 2.
So brilliant. We said that there are some exceptions, and one exception to the rule is that D8 metals tend to be happy with 16 electrons, they tend to be square planar. And so for every rule or empirical trend, there's an exception, and D8 square planar metals are indeed one exception. So I'll leave it to you to think about the other palladium in this case. Yes. Rico.
So I just want to confirm, so when you do like the electron counting on the right, the hydroxide is out because it's bridging.
Well, yeah, so this is a good question. So you can, if you have no further information, you can count this as this way, or you can do it this way. Now, one of the ways will get you into something that will probably make you uncomfortable. You will get to an answer where you have a palladium 1 and a palladium 3, and you'll think that doesn't seem so stable. I wonder if the alternative formalism of palladium 2 to palladium 2 is a better descriptor, and then you would be right. But based on everything we've covered, it's if you weren't sure what to do, then you're probably not alone. Again, I think sometimes it's, when you get to the end of it, you have to step back and like holistically say, does this make sense? Particularly for these polymetallic, polybridge things. If they're in, if they're in close bonding interaction and they have very different oxidation states, then it's possible that you did something where you like counted all on the left side, L-type ligands, all on the right side, X-type ligands for bridging. And it would just give you very different, different formal oxidation states. And that's not the end of the world. I mean, again, it's like, that's an honest, I wouldn't even say it's a mistake. It's like, that's an outcome that can happen if you're not sure, but as you build your intuition, you'd know to avoid drawing that as an answer. Okay, we'll talk now about another wrinkle here. So, one of the themes of electron counting is that age-old tradition is that faculty members and TAs provide the rules, and then they try to find the most extreme questions for homeworks and for exams that have all the exceptions to the rules. And so then you need to learn all the exceptions. Again, it's an age-old tradition. I think for homework, we will sometimes push the envelope and have wacky examples. For exam, it will be pretty cut and dry because I've certainly been in the situation where you get something on a midterm or exam, it's like really strange and it just takes a lot of time because there's like different ways you can think about it, and that's not a great use of an exam. It should be more of an assessment. Okay, so we'll talk about metal-metal bonds, and this is really nicely set up for us by Alex. And so metal-metal bonding often comes about when a metal has an open shell. And so this was the case with ferrocenium. The metal has an open shell, and it's unstable in that state. And so it can form a bonding interaction with another metal of open shell. And by sharing electrons, they can get to a more stable bimetallic adduct than either is in isolation. There's a formula for allowing you to predict the number of metal-metal bonds from a given molecular formula. And essentially what that formula is, it's predicated on the 18 electron rule or the 18 electron empirical trend. It assumes 18 electrons per metal. So M is the number of metals. And then it subtracts the total number of valence electrons, so the number of electrons that are coming from the ligands, and then divides by 2, assuming that the metal would like to find another metal to form stabilizing interactions. Again, I think this formula, it's fine to just memorize, but it's better to understand where it comes from. So in terms of electron counting, metal bonds count for 1 valence electron per metal. So let's take an example. Dicobalt octacarbonyl, or just cobalt carbonyl. We'll work this through using the formula above. There are 2 metals. Cobalt is 0 is D9. There are 8 ligands, each bringing 2 electrons for a total of, per metal. So it's this times 2 for a total of 34 electrons. This is N, M equals 2, and then we can plug into our formula 18 times 2 metals minus 34 valence electrons divided by 2 electrons per metal-metal bond gives us 1 metal-metal bond. Yes.
8 times 2 times 2, 32. The plus 2.
Sorry, what did I do? 8 times 2,
16 times 2 is 32.
all right. It's the problem of copying mindlessly from my notes and not thinking about, So it's meant to be 2 times 9 electrons from the 2 metal centers. And that gets us to 34 electrons. Does that look better? Sorry about that. So what would that look like then in terms of connectivity? Let's build it from the inside out. We know that there's a cobalt-cobalt bond. And this is always confusing when you have cobalt carbonyls because everything just is different types of CO. It doesn't look very nice. Bear with me, please. And in fact, though you have no reason to know this, but if you do happen to know this and you're just into these metal carbonyl complexes, this is a bit of a simplification because this complex actually exists in equilibrium between two states as shown here. And whether in this state, whether there's a metal-metal bond is the topic of some debate and study. Okay, any questions on that? Okay, more special cases, so to speak. Here's another ligand type that faculty and TAs like to torture students with. These are the nitrosyl ligands, NO. And they're very strange. This is one of these things where like people always like to have nitrosyls on exams, and I've still yet to encounter a single nitrosyl in my 20 years of doing research in organometallic chemistry, but I see them on exams all the time. So why nitrosyl is an unusual little ligand is because it can have two different coordination geometries, and the different coordination geometries, you end up doing electron counting in different ways. So the most common form of a nitrosyl ligand that you'll encounter is the linear form. And it's isoelectronic, isostructural to CO ligand that you're now hopefully getting a little bit more familiar with. And so I said that the linear and bent nitrosyl you count different ways, and rather than trying to just mindlessly memorize how to count it, I'll try to give you some mnemonic or heuristic for at least how I like to think about it. And so the linear NO, when you dissociate the nitrosyl ligand, what you would get to is something that looks like this with an overall positive charge, where the nitrosyl and the nitrogen is linear. So the nitrogen is sp hybridized. That means it's forming a triple bond to oxygen. And then I think from here, it's not too much of a stretch to think, okay, it's kind of like an L-type ligand, but it has this weird trait of bringing positive charge. And that's indeed how you can electron count it. It's L-type, but just has this asterisk of it brings a positive charge to the party. And let's play that out with bent nitrosyl. Here, the nitrogen is clearly sp2 hybridized, right? Because it has this nonlinear geometry that in an idealized situation would look like 120 degrees. And so if you dissociate this form of the ligand, you see that it would look anionic. And indeed, you can then get to 2 electrons minus 1 charge. This one you count just like an X-type ligand, whereas above you count like an L-type ligand with the asterisk, and the asterisk is that it brings this +1 charge. Okay, we'll see examples of this. So if it's a little confusing now, then I can answer questions after we go through an example. And then another special class of positively charged ligands are these tropyliums. And so I'll highlight the connection here between the tropylium and other isoelectronic ligands. We know from one of the first things we learn as undergraduates in organic chemistry is aromaticity, which follows what's the formula for aromaticity? Anybody? 4n plus 2, I heard people whisper. And so all three of these ligands, CP, benzene, tropylium, share that they have 6 valence electrons and have this form of aromaticity. They're all thus isoelectronic, but in terms of electron counting, they're different. You have one that's has an X type in CP, one that's overall neutral in the form of benzene, and one that is overall cationic in the form of tropylium. Don't get too bogged down on these details. The likelihood of encountering a tropylium is not that high. I think focus on the more commonly encountered ones first. So let's now take a look at problem of the day. Number 1 from, sorry, I'll try to avoid doing this jumping between days. So here we have a chance now to practice electron counting with NO. If you encounter there are some guiding principles if you are in a situation like this and you just encounter a molecular formula that has a nitrosyl ligand, determining whether it's bent or linear. But I think as a first approximation, if you're not given more information, you can assume it's linear because most NO ligands that you encounter in the free world will indeed be linear. And if you want to know more than that, then there's a review article that I had on that provides you some more of a framework for thinking that through. So take a look. Now we have this interesting molybdenum tris CP nitrosyl adduct. And this Al was, I think, setting the stage for this type of complex. Each CP has different hapticities. Okay, so that already makes it a very structurally cool molecule. Is the linear NO ligand linear and bent in this complex? I just gave you a strong hint. And then what is the oxidation state based on your answer to the first question? Okay, take a minute or two to think about that. And you know, if you're bored, then do a double check and make sure that it comes, do the electron counting to make sure that it comes out to 18 electrons. Don't just take our word for it. All right, so Jiakai, give me some thoughts here. So first we've got molybdenum. It's got these 3 CPs. So let's try to draw something that looks reasonable. Here's the eta 5. It's not a good eta. Eta 5, and then according to the question, we need to have one that's eta 3. That could be this, and then one that's eta 1. Oh, what happened there?
Scroll up.
Yeah, interesting. Let's try this again. Okay, there we go. Sorry about that. Thanks for catching that. Okay, so these are the 3 different hapticities. Was this what you got, Chiakai?
Yeah.
Eta 1, eta 3, eta 5, and then the last ligand is in NO. And so what did you get for this one?
If you consider the metal as D6, and each ligand will donate 1 electron, 3 electron, and 5 electron.
Okay. Okay, so you're saying molybdenum 0 is D6.
Yeah.
You've got 3 X-type ligands, so you know that molybdenum is going to be at least +3 oxidation state. Well, it could be plus, it's got at least that ligand set around it to consider. And then walk me through what you were thinking. You said, so you're using the neutral counting method, I think.
Yeah.
Is that right? Okay, so
So each ligand will donate in like 1 electron, and other one is 3 electron. The final one is 5 electrons.
Yeah.
The total is like 9 electron in total. So it's 15 electron, and use 18 to. So the NO will donate in like 3 electron in total. So should be a linear type NO.
okay. Yeah, so this is one, there are some cases where the covalent method, I think, is a little bit faster, and this is one, but let's just do this also, since we're teaching the anionic method, we'll do that as well. So we've got 3 X-type ligands. This is XL2, this is XL, and this is just X. So we've got -3, we said linear.
Something.
I think it's working. Oh, it's fine. You know, here. If I draw.
Yeah.
And then linear NO, which is L type, but +1. So we can do this quickly. We've got molybdenum. What was your oxidation state assignment, Jiakai? You said molybdenum.
Now is +2.
+2 before. And then you've got 1, 2, 3, 4, 5, 6 electrons around it. 6 times 2 electrons. 12 electrons from the CPs. And then you said 3 electrons, but we're gonna just say 2 electrons for our counting system. We've got D4 +2 +12 is equal to 18 electrons. Yeah, Eugene.
So confused how we got to the conclusion that NO is linear.
Well, I think that we got there because I gave you the hint that you should think that it's linear until you hear otherwise.
Right.
I think I can give an alternative explanation.
Go for it.
So whether the NO is linear or not, if you use the anionic counting system, it donates 2 electrons. And then if you have the 3 CPs with different hapticities, you would add up to 2 + 4 + 6, which is 12 electrons. So all of your ligands, they give a total of 14 electrons. And we now know that this complex itself is an 18 electron complex. So your metal is going to donate 4 electrons.
But how did you know that the complex was 18 electrons?
Oh, I gave it as a hint.
Oh, sure, yeah.
Good point. So you know 4 electrons on molybdenum after all of your again charge. Then you know it's +2 oxidations.
Thanks.
I have a question regarding
Sure.
the metal bond. So when we do the electron count for like metal bonds, do we add 1 electron to the total electron counting to the metal center?
Yes, so if you have a bimetallic, so in the case of that dicobalt, if you count each side separately, if you just divide it in half and you count it, you get to 17 electrons. If you form the metal-metal bond, then each metal is is seeing like half of that bond. So that's where the one electron. So anytime you have bimetallic complexes, you've got to count both sides of it. So it's like a +1 for both sides. They each benefit from forming the bonding interaction, so they each get a +1 electron.
Wenji, could you explain your thing again? Because I'm getting 15, but like without the NO, because it's molybdenum, you assume 3, right, at first? With
You
the
actually
3,
need to assume the oxidation state of that.
you don't need to assume.
Because I provided the total electron counts to be 18 in, I think the first sentence. If I did the product, right? So the complex itself is 18.
Yeah, but okay, let's say you take off the NO for now, right? There should be, I'm getting 15 electrons without the NO, is that wrong? Or
Which method are you using? Is it,
the anionic?
yeah, ionic.
You're using the ionic method.
Ionic actually use the NO is 2 electrons instead of 3 electrons. So if you use the neutral method, NO is going to be a 3 electron donor if it's linear. But if you use the ionic method, no matter if it's linear or bent, it's 2 electron donor. But then you carry a charge on it.
Okay.
So you could do this exercise, Kevin, of like, let's imagine there's, because this is what you're asking. So let's imagine we don't do that. Then you have molybdenum +3,
Yeah, and then I'll fix it to 18 now.
and then you will have, this would be D3, and then you have fixed ligands. So it's going to get you to 15 electrons.
Yeah, so we need 3 more. Is that,
But to get to an 18 electron count, you need 3 more, right?
yeah. And is that not the bent configurations that would give you 3 more?
Well, the way that, so this is one of these, again, it's kind of a wonky formalism. So because you have, so from here.
Yeah.
Then you coordinate the NO.
Yeah.
The NO is positively charged. So what that does in terms of the formalism is it changes the oxidation state of molybdenum to be +2.
Oh, I see. Okay.
So it becomes
More.
D4. And then you get one more 2 electron interaction. So you end up getting to 18 electrons.
Okay, thank you.
Although I realize it's very confusing. But probably what you might not have accounted for is the oxidation state adjustment that you need things to make.
We can do the covalent and ionic, like either one of them and take them, right?
Yes. Well, I mean, what we would grade is the answers, so you can get to the answers. No matter which way you count, you shouldn't have different oxidation states. You shouldn't have different overall electron patterns.
I think according to the Harvard book, actually for especially ligands with different hapticities, the covalent method is easier to use. I think especially in this case, if you use the covalent method, you can derive the NO to be a 3 electron donor right away.
Yeah, it's not without its advantages. I think it's a little bit less intuitive, but it is not without its advantages. I think the camera got a little bit out of focus. Okay, with the time we have left, we'll jump into, we'll cover as much ground as we can on the day 3 notes, which is focused on periodic trends and developing this conceptual basis for being able to anticipate, rationalize reactivity trends that we'll then see in the context of elementary steps and catalysis. I want to draw your attention, one of the readings that'll be available for you on Canvas is a really nice tutorial from Pete Wolzanski. It's just from last year. I think he spent part of his sabbatical assembling this, and it's directly geared towards first-year graduate students that presents some of what I'm going to talk about today, these periodic trends, in a fairly engaging way. It has some really nice summary charts, including this periodic table that has overlaid on it a number of useful values that is included on one of your handouts from today. So one of the first things to get used to in operating in the D block as compared to the S and P blocks that you grow up learning as chemists is that unlike the S and P block, that trends that you observe are not necessarily continuous across the entire transition series, entire D block. So the trends that we're talking about are best to consider, let's say, within a certain row or within a certain group, i.e. column. And then another point that we already touched upon is that there are some trends and properties that are different, or it's not an apples to apples comparison if you're comparing the element itself, it's in the gas phase, versus when it's in a complex and it has a coordination environment and it has an oxidation state. So we've talked about electronegativity as a readout of orbital energies, and d orbital energies also go hand in hand with ionization potentials, so they can indeed be estimated from ionization potential. So just to help orient us, as increasing ionization potential versus decreasing ionization potential. So which way, left to right or right to left or top to bottom, bottom to top, which way would you expect there to be a consistent increase in ionization potential across the D block? Eugene?
Left to right.
Left to right, okay. Do you want to explain your reasoning quickly?
Well, I suppose the more electrons you put on there, the easier it'd be to take one off, because there'd be more shielding of the nuclear charge.
Yeah, it goes hand in hand, thanks Eugene, with electronegativities. As you go further right, you generally encounter more electronegative atoms that hold on to their electrons more tightly. This is why it's more common to see titanium in its +4 oxidation state than it is to see palladium or nickel at +4 oxidation state. Good. So let's then apply this to a specific example, zirconium-2 versus palladium-2. Which would be easier to oxidize? What do you think, Amy? Zirconium, okay? Why?
Yeah, just for
What
that.
I just said.
Yeah.
And then equivalent ways to describe this would be to say that zirconium is more electron rich or more basic. Okay, now let's, within a column, talk about trends going up and down. So if we're talking about forming high oxidation state species, so when we say high oxidation state or high valent, typically we're talking about things that are +3, +4, or above. So let's take the specific case of nickel-4 versus platinum-4, which is easier to form. Anna? Platinum-4, okay. Why do you think that?
Because it's less like holding the electron less tightly.
Yeah.
than nickel.
Any questions on that? All right, now let's talk about atomic size. So, and we're going to make comparisons first row, second row, third row. So if it's easier for you, you can just stay within one column or stay within one group. and ask, as I go down nickel, palladium, platinum, what is the trend that I observe in size? So let's do the first one, first row versus second. Mately, what do you think? Which has bigger atomic radius? Second row, okay? Now let's compare second and third row.
Third,
Third row is what?
or have the higher. Would it be like higher side?
I think your intuition that you've developed in the S and P block is to, as you go down, get bigger. But in fact, the second and third row metals end up being almost the same. And that's because you're having competing, not necessarily competing factors, but there's additional factors at play in considering the D block. So in going from first row to second row, your intuition of higher quantum number of valence orbitals, meaning larger atomic size, certainly holds. But then as you start to pack more and more electrons around these atoms, you have additional effects that come into play. You have something called the lanthanide contraction, which is you start to really pack in the nuclear charge gets higher and higher as you get to third row elements. So the nuclear charge in going from second row to third row is much higher. And that means that the electrons that are being held in more and more diffuse orbitals are not as efficiently shielding that next electron that comes in. And so there's this effect where each electron is feeling more and more effective nuclear charge. And you also have an effect called relativistic effects, where the angular momentum that some of these high energy electrons are feeling is sufficiently high that the velocity of the electron approaches the speed of light, which causes the electron's mass to increase and the overall diffuseness of its orbital to be small. Those details are not necessarily so important, but I want to give you a flavor from a basic science perspective to where these trends come from. And then when we're talking about navigating left and right on the periodic table, we have to make some caveats. So we would say for complexes of groups 4 through 7 with the same charge and the same oxidation state, then it is true that size decreases as you go left to right. But again, I think the reason you have to add these caveats is because now you're in the D block and not everything has these clear trends. Let's talk about metal ligand bond strength. This is going to be the heart of all of these catalytic reactions that we're going to cover. And we had a primer for this in one of the first lectures, which is that for metal ligand bond strength in general, they're weaker interactions with first row metals and stronger interactions with third row metals. And this is certainly true with carbogenic substituents. Now, if you're thinking carefully about this in terms of what you already know, you'll note that this trend is in fact opposite of the trend in the main group. For example, carbon chlorine versus carbon bromine versus carbon iodine. So the origin of this trend, and this is what the way I learned it, and then I realized that this is in a sense a hand wavy argument. So we'll look at this with a little bit more granularity. The origin, at least in part, is the spatial overlap of the metal with the ligand orbital. So what exactly does that mean? We'll see in our next problem of the day. And then you have these considerations of the energy levels of the ligand orbitals, the energy levels of the metal orbitals, and this phenomenon of radial nodes, which I think, again, is pretty intuitive if you see it drawn out, and is not that intuitive to just talk about. So I would direct you, if you have an interest in some of these periodic trends specifically, there's a really nice review that touches on these. Even though it's in a computational journal, it has a really clear framing of some of these trends for organic chemists, and this will also be included in today's reading. So now let's zero in on what we mean by orbital overlap. And to do that, we're going to take a deep dive into the atomic orbitals, and we'll review some things that you probably haven't thought deeply about since Gen Chem, which is fine. That's why we're here. Okay, so as our jumping off point into problem of the day number 2, let's consider these quantum numbers that are defined by the orbitals in question. So for example, for any NL orbital, such as the 4D orbital, we have our principal quantum number, in this case 4, our angular quantum number, which in the case of a d orbital is 2. And does anybody remember what this defines in terms of the total number of nodes of these orbitals and the number of angular nodes total first, Julian?
So if it's D, then it means there's 2 angular nodes.
Okay, so the number of angular nodes is L, as we
So
defined it here,
L equals 2 in the case of
and
a,
equals 2 in this case, yeah. And then what about the total number of nodes?
it's gonna have, I think, 1 spherical node. So
Okay, so
3 in total.
in general, it is the principal quantum number minus 1. So it's equal to the number of angular nodes plus the number of radial nodes. So that's where you were saying there should be 1. In this case, you're 4D, so your total number of nodes is 3. You have 2 angular nodes, which means you have 1 radial, if I understood you correctly.
Yeah.
Perfect. Okay. So now problem of the day, now we're set up for problem of the day number 2, which asks us to draw a 4D orbital. At least the 3, if you're very artistic, go for it to draw it in 3D. I'm not gonna be able to do that. I'm gonna draw a 2D projection of it, but hopefully you appreciate that it exists in 3D. So take a minute to think about that, and then we'll discuss it as a group. And so for this question, just to directly jot down what Julian just told us, with 4D, we just said we've got 3 total nodes. We have 2 angular nodes, and we have 1 radial node. I'm going to draw this 3D projection, or 2D projection as such. Oh, am I giving away too much already? I won't. for this specific problem, I'm not gonna ask for volunteers because it would involve having you come to the board and it's not really easy to describe. So, I'll explain what I'm doing here. So we have two angular nodes, which I'm going to represent as I have here with these two lines, and then my one radial node. And that's pretty much it. That's the question. And then it's just about filling in the electron density. Hoping my Apple Pencil doesn't die here. Bless you. Whereas these, they don't really, as you're filling it in here, you'll see it doesn't really resemble an orbital, but then as you start to fill it out, it looks a little more friendly and familiar. And why I like to just take the time to draw out the 4D orbitals is that anytime you ever see the D orbitals introduced, it's always the 3D. And so we have a really strong intuition about what 3D orbitals look like. And we're familiar with the friendly looking donut of the DZ squared orbital. And we can draw those like the back of our hand, even if we haven't covered organometallic chemistry. But the 4D, I think, don't automatically, again, this is a 2D, oh my gosh, this is terrible. It's not, it's definitely needs to be symmetric, asymmetric, so you know that part of it. But hopefully this gives you the gist. So why do we take the time to do this? It's because anytime you will see d orbital diagrams drawn out, it will be the 3D for simplicity. But there's a lot of good action that's happening with the 4D and 5D orbitals. And the key point in terms of this connection, this connectivity to bond strength and orbital interactions is, look what happens when you're trying to form a bonding interaction over here. This is kind of what the 3D systems look like. The 3D electrons, orbitals on the metal are trying to form a bonding interaction with the ligand, but they're struggling because they're buried in the sea of S and P orbitals that they're trying to fight for to break free to form a bonding interaction. In the 4D and 5D, because of these radial nodes, where the big lobes of the orbitals are, project much further into space. And now these orbitals are free in space to form strong bonding interactions with the ligands, and they're at the appropriate energy levels to do so. And so that ability at the 4D and 5D to be past this spherical, quasi-spherical shell of shielding and electronic repulsion is really a key to the strength of the bonding interactions. And I think it's just helpful, at least for me, it's helpful to see that depicted visually. And anytime you hear better orbital overlap, you'll know what that means, that traces back to the presence of radial nodes. Any questions on that? I realize I went through it quickly.
If you were to add one more angular node, how would you do it? Would it be diagonal?
If you were to go, so for the, what are we talking about specifically? Sorry, to add one more angular node or one more?
Yeah, angular.
One more angular node. So then you're talking about
Maybe an F.
an f orbital.
Yeah,
So these are
Probably help you this one.
yeah, I mean, the F, do you know the shape of the F orbitals, right? They're kind of these like, I don't know, they look like figure eights kind of. Don't really know how would you describe what the F orbitals look like?
I think for d orbitals, some of those, you can think of them as going to same directions as axes as in the three-dimensional.
I think that, yeah, the most intuitive, so we can talk about this after class. The most intuitive case study will be the 4F, because that will have 0 radial nodes. And so it's just a buildup of radial nodes that are intersecting the origin, right?
The mochi donut.
Yeah, mochi donut, okay.
So it has
I'm gonna
8
click
different lobes pointing to different directions. That's the simplest set. There are different ones.
And this too, I mean, like, this is a relatively simple case study, like how you, for example, how you draw the angular node when you're talking about DZ squared orbitals is different than when you're talking about the DXY, for example, but we can talk more about that. Okay, hard, soft, acid, base theory. I won't say too much about hard, soft, acid, base theory. Other than you will hear this mentioned, and it does have some explanatory value. It views the world of bonding interactions into a continuum, but with two extremes, so-called hard metals and ligands and soft metals and ligands. And hard forms stronger bonding interactions, and soft forms relatively strong bonding interactions, and the hard soft is relatively weaker bonding interactions. And this ultimately comes to orbital overlap. Soft metals and ligands have relatively diffuse orbitals that are highly polarizable. So for ligands, think things like phosphines, sulfides. And for the metals, think second and third row metals. Hard ligands, think small, charge dense entities, fluoride, chloride, alkoxides. And on the metal side, think first row metals, earlier metals. And so you'll hear this sometimes of, you know, what is the driving force for this interaction? Oh, it's a soft interaction that's forming a strong bond. It's a hard interaction. It is useful as an intuition because it will tell you, it will allow you to predict things like in a Suzuki-Miura coupling, when you form a palladium hydroxide species, you'll think that is not super happy because the ligand is hard, the metal is soft. So the ligand would prefer to get transferred to something itself hard, like boron, and boron would be happy to transfer its ligand, i.e. a carbogenic group, to palladium to have soft. So it is useful, although it's mostly descriptive in terms of how it's useful. Okay, let me just get through this last table, and this will be a natural stopping point here. So building up here, we're going to have different levels of treatment to go from molecular formula to 3D geometry. And the first and simplest, and historically the first treatment to come online, is called VSEPR, or valence shell electron repulsion theory. And this is effectively, you have a number of ligands around the metal. These can be viewed as electron pairs. And these electron pairs want to navigate to points on the surface of the sphere that are maximally distal from other electron pairs on this sphere. And this then constitutes the set of preferred geometries. And you can imagine this had its day in the sun and was useful for a period of time, and now we have more sophisticated treatments for how to think about this. But to walk us through it, for two coordinate species, you have two predominant different flavors, linear and bent. For three coordinate species, you have a couple different flavors here, trigonal planar, which is the most common, and then two specialized forms, pyramidal, which you can view as similar to ammonia, or T-shaped. Here's an example. Although these are specialized, they're still, new examples still appear in the literature. So here's one from now a few years ago from Pat Holland's group. An interesting nickel, NAC-NAC ligated nickel species that adopts a T-shaped geometry. The bread and butter, the geometries that we're going to interact with most in class are the ones that are denoted here with a red dot, square planar, tetrahedral, and octahedral, and maybe to a lesser extent, trigonal pyramidal, square pyramidal. So to walk us through that, four coordinate species will come in two flavors, square planar and tetrahedral. We've already encountered both already in class. Five coordinate can be trigonal pyramidal or square pyramidal, like iron carbonyl and vanadium oxo-ACAC respectively. Six coordinate almost always is octahedral, but there are some exceptions. And so let me go through and fill out some of these. So square planar, we have classical example that we'll cover more later in class. Some folks, feel free, if you know the name of this, to just shout it out. Any takers? Wilkinson's catalyst, thank you. Tetrahedral, things like nickel cod, titanium tetrachloride, tetrakis. Octahedral complexes, we covered the Werner complexes. Aqua complexes. And then there are some exotic variations on this. So for six coordinate, and actually this was one Ningxi, I think, asked about in the context of the Ferrocene discussion, or had a comment about, which is trigonal prismatic. So this you will very likely never encounter in your life, but it's interesting to know that it can exist. And I don't know if anybody off the top of their head knows any, maybe Ningxi, because you brought up this geometry. Do you know off the top of your head any complexes that adopt this geometry?
Not really.
Not really. Okay, that's okay. Does anybody? So for our group, it's something maybe we might, somebody might know, because the hexamethyl or permethyl tungsten is one of the prominent examples of this type of geometry covered in this paper.
The crystal structure of the beryllium ligated nickel, which is developed in Simon Aldrich slab. It's also
Simon Aldrich, yes.
It's also a trigonal prismatic. But you need to read them through.
And I think this one is especially interesting because the ligand set is very simple. Like you can imagine, and that's the case of this other example that I have from our chemist of the day, who is not Japanese. This is Jamie Neely. From St. Louis University at PUI, trained with Tom Robis, and sulfuric and working base metals. In this example from the Neely group, the geometry of the ligand by virtue of being tetradentate and is constrained. And so it can force manganese to adopt this pseudo trigonal prismatic geometry because of the ligand architecture. But the tungsten hexamethyl case is a special one because the origin of that is predominantly an electronic phenomenon rather than a chelation effect. And so, and then on, you can build up higher coordination numbers, and I won't say more about that, except to tell you that there is a world beyond 6 coordinate. And we, in fact, isolated some 7 coordinate species ourselves, and there's a whole litany of geometries like capped octahedra and so on and so forth that we won't talk more about. But what this framework, the VSCPR framework, doesn't allow us to rationalize or predict are some of the hallmark features of coordination complexes such as color, magnetism, electronic configuration. And so that's what we will build up from this point forward through crystal field theory and ligand field theory. So that's where we will pick things up on Thursday. Thanks, everybody.